Hi guys, welcome to another video. Today we're going to look at a couple of things. Start off with some more basic notation that we didn't quite manage to, I suppose, touch on, and then expand that into looking into matrices. We'll look at some very basic properties of matrices. We won't go as far as to look at matrix and matrix multiplication. We'll look at scalar multiplication and a couple of other transient properties that are worth noting. In the follow-up video to this, I will cover off aspects around matrix multiplication. We'll look into how we can use matrices to help solve some equations. For example, in our linear regression case, where we're going into multiple dimensions. So those will follow on after this video, but today we're going to focus specifically in the area around very straightforward matrices. So let's get straight into it. So you would remember from previous videos that we did, I used a couple of different notations before. Today I'm going to expand on those notations. We're going to look at what are number sets, you guys have worked in these number sets before. For example, so if I show you this number set, which is our real space, and what the real numbers are, they're essentially anything from minus infinity all the way up to infinity, right? So it's every single number that we have that is a real number. We're not going to touch on imaginary numbers. There is a totally other section. If you are interested in that, please do hit me up and I'll give you more detail around that. However, so the real numbers are this. Now, you'll note that when we talk about some of our real numbers, for example, when we talk into multidimensional or vector spaces here, I'll say, hey, I've got this vector and that's contained in the real number space at D, right? Now, what that D means is it's D dimensions. So, for example, if I break this up a bit more, X could, for example, look like, we might have a vector, which is, x1, x2, x3, and all the way to xd, right? And what that's saying is, for all our xi that's contained in our vector space x, xi is contained in the real number space, right? So that's essentially what this is saying in shorthand, is that, our vector space, our vector x is actually contained within a d-dimensional real number space. There are a couple of others. Now, I'm going to make a correction to something I said in our live stream about integers. I actually denoted it with an I. Actually, the truth is denoted by a Z, right? So here's our real number space. And our integers. What the integers here are is every number, again, from minus infinity up to infinity. The only difference is these are all of our whole numbers. So unlike the real numbers, which could be anything in the entire number space, these are only whole numbers. So we won't have anything such as pi in this. What we'll end up having is things like our 0, 1, 2 in the positive zone, as well as minus 2, minus 1, 0 in the negative space, right? So it's anything like this. So if you see, if I ever write this notation where I say, I is contained in our, our integer space, what that means is that, I is a whole number. And we'll use this quite a lot for our indices, when we want to talk about, here, for example, this I is in this integer space. Last but not least, one other number set that I want to talk about is the natural numbers, and I mentioned this in the live stream, right? The natural numbers here are essentially everything within the 0 to infinity scale. So it's everything that is positive, okay? So it's a subset of the integers. So actually, you could even write this like this, where these are contained in our integer space, right? And they are a subset of our integers. So these are the number sets I wanted to kind of mention very briefly. We will use our real numbers a lot and our integers. More importantly, for our indexing, it'll be our natural numbers quite a lot. So this is an important kind of set of numbers to be aware of. Okay. Now, a couple of further notations to touch on, and I already kind of did this a minute ago. If I ever write if I say, A with a single underscore, I'm actually talking about a vector. So it'll be a vector, A1 down to AN. If I ever talk about a with 2 lines underneath it, then I'm talking about a matrix, right? A1 1 to A1n to AMN, AM1, right? So just again, a little notational piece is, where I have a single underline, I'm talking about a vector, double underline is a matrix. Now, in some books and some lecturers might actually always use a lowercase here to represent a vector. In most of the notation we're going to be doing, it will be just lowercase. So anything that I use as a lowercase is your vector. Anything in an uppercase will be your matrix, but I will always use the underlines to signify the difference between the two. So that's something quite important to note, just a small bit of notation. Okay, stepping through, let's just talk about some commutative laws around matrix addition and subtraction. So simple arithmetic here. So for example, if we have 2 matrices, both of the same size, so this is an M by N, and we have a B, which is a M by N. Oops. N by N. Well, you can rewrite this to be B plus A. So this commutative law exists, and it is true. This is quite important. It will form the fundamentals of some of the algebra that we'll look at. Also, for example, in that sense, you could always take this down to another level. If we go, well, we have A plus B is equal to some C, right? Well, say we don't know what the values of A are, we want to figure that out. Well, hey, that's quite simple to do. A is equal to C minus B, right? So we can move that over. And this is another important extension worth kind of knowing. So these two form some very basic arithmetic for our matrices. Right? Now, you can do the proofs of these. It's quite simple. Everything and anything I talk about, you can kind of simplify it down to like a 2x2 matrix, right? And from that 2x2 matrix, you can pretty much prove all of these through some mathematical proof. But I'm not going to do that in this video. There will be links at the end. There will be a video link that you can go and follow that will go into much more detail around matrices. It is a very large topic, and I'm only really going to touch on a small section of it. Okay, so moving along, let's talk about some other interesting rules. We're going to talk about scalar multiplication. What do I mean by a scalar? A scalar is neither a vector nor a matrix. So, for example, 2 is a scalar, right? As is 3, so it's any number, and it can be 3.3, right? Any number, and we're going to say that we have this scalar k, right? Let me write it in lowercase. So we have the scalar k. It's contained in the real number space. Okay. Now for all scalar k in the real number space, if we have this, right, k times, let's make this lowercase, k times a is equal to b, then if we want to solve for a, we can just divide b by k, right? So here's another quite important little rule to remember. Now, another one here to kind of keep in mind is, so if we have a plus b, well, that is equal to ka. Apologies for missing that out, right? Ka plus kb. Okay, another quite important little rule to kind of keep in mind. So we've got a couple of rules around scalar multiplication that you should know. It is quite it's quite good to know. Okay, moving on from that, another one to kind of keep in mind is what we call a transpose. So if I have this matrix, now I can rewrite this matrix in another weird notation that you wouldn't have seen. So let's say that this is a capital N by capital M matrix. Then the elements within it is, as such. So if I generalize that, so the transpose, so if I was to transpose this matrix, written with a T, capital T on top, well, that then has all the elements are flipped, so that becomes an M by N matrix. The mechanics behind this, the geometry, if you want to visualize it really, so let's say that we have this here, this matrix here, where we have A11 all the way down to A and M, A1M, and A and 1. Let's make sure I wrote this the same way as written it before. Okay, right. Well, let's make this assumption there. Well, what we're going to do is we're going to take this bottom triangle here of values and this top triangle here of values, and we're going to switch them around, right? So those are going to go over there, and these are going to come over here, right? And that's the physical mechanics of it, right? Anything on this diagonal, as you can notice, it's not going to change. So if we have interestingly, if we have a diagonal matrix, so that is a diagonal matrix is where all the values on this diagonal, that we have values on this diagonal, nothing in the coordinates in our triangles. Well, then there's this rule that says the transpose of A, if it's a, well, let's use a different word. So if the transpose of B, which is a diagonal matrix, is actually equal to B. So here's another little rule. So for diagonal matrices, this can also be applied to what are called symmetric matrices, right? Okay, and a symmetric matrix, similar to a diagonal matrix, is where the two triangles are equal. So I'll give you an example. If I was to write this out for a 2 by 2 matrix, for example, if I have A11, A12, A12, A22, right? Well, the bottom triangle here and the top triangle here are the same. So when we swap these two around, well, they'll remain. So this rule applies for both diagonal matrices and for symmetric matrices. Right. And actually, you could argue that every diagonal matrix is a symmetric matrix. Right? So here's a very brief run through of some properties of matrices that are worth noting. I will say that the transpose is really is only ever used for a couple of instances. We're not going to really use them. You're never really going to use the transpose for more than just as a mechanic for other things, such as the determinant or for calculating the inverse. More importantly, actually, you're not really going to use the transpose for many other things, but they will become useful later on. There are other properties we'll cover off in the more detailed video next. But if you have any comments, do either put a comment in the comment box below on the video, or send me a direct message, and I can cover off more detail or add in more detail into my next video. Thanks, guys. Hope you have a good one. Speak to you soon.